Hi everyone, I am Shaptoshi here and I welcome you back to our course on machine learning using Python. So last class we have looked at neural networks. So we have essentially looked at some basic terms about biological neurons and how that has motivated computer scientists to come up abstract models of computations. One such model was perceptron, and we saw the connection of perceptron with machine learning, that it can do linear classification problems well. So today we are going to delve more into perceptron. So first of all, we are going to look at decision boundaries and perceptron. We will look at the need of layering of perceptron. We will look at, what is the difference between perceptron learning and gradient descent. Okay. So if you remember, perceptron learning also tries to find parameters of a model, and gradient descent, we have discussed in our gradient descent lecture, can work as a master key to find parameters of a model. Okay. Then we will see that whether perceptron is indeed quite generic model of computation and can attempt simple problems like linear regression and logistic regression. Okay, so let's get started. So, if the perceptron is given a problem like this, okay, so there are two classes and you can draw a straight line and separate them, the perceptron can find such a decision boundary. So if they are linearly separable, basically this is a straight line and the straight line may be represented by W1 and W2. So step by step, this perceptron can find out the values of W1 and W2 through that perceptron learning algorithm. However, what happens if the decision boundary is not linear? Something like this. So perceptron not work over here. What about if the decision boundary is complex? So a combination. So something like this. So one side I have a nonlinear separation boundary like this. Another side I may have a circular decision boundary like this, which is more similar to your radial basis kernel. So here also your perceptron won't work. Okay. All right. So let's look at some other example as well. So if you remember, we told that your MP neuron as well as your perceptron can implement simple logical operations like AND, NAND, all these things. Okay. So let's look at XOR. So you are all familiar with this XOR truth table, right? So this is your inputs, all are binary, and this is your output, this is also binary. So anywhere you have even number of zeros or ones, so that is 0, otherwise it is 1. So first of all, we will try to inspect whether they are linearly separable or not. So let's draw them in a scatter plot and see. So these are your zeros and these are your ones. Okay. Now the question is that can I somehow draw a line which separates these two classes? So if you pause for a moment, you will realize that no, this is not the case. I cannot draw a line and separate them. Probably I need two lines for that. Okay. And standing at 2020, this may seem a very simple problem to you, but in 1969, there was a very famous monograph by Minsky and Seymour on perceptron, where they highlighted this as one of the major weaknesses. Okay, so which kind of stalled the research on perceptron for quite some time. However, intuitively, people thought that if one perceptron can draw a line, here what we want is two lines, that's all, right? And if we can use two perceptrons to draw a line and somehow can indicate that this region is within these two lines and this region is outside of these two lines, then perceptrons can solve such a problem. And this is how a perceptron can solve this problem. So we will not worry too much about the working of this perceptron right now, and so we will not worry about the weights and all. But essentially what we are telling is that this perceptron will draw one line, maybe this line, and this perceptron will draw another line, maybe this line. And finally, this perceptron will consider or compare them and see that whether this is within the line or this is outside of the line. Okay. So there are various biases that have been used. As we have said, that biases have the same concept as intercept and can be trivially considered as another input neuron. Okay, so let's look at some other example. So here what we want is this shaded region. This we want to call as the one class, and outside of this two line we want to call this as 0. So very similar to our XOR problem. Okay, so this line we are calling this as S1, this line we are calling as S2, and this is X1, X and Y, these are your input variables. Okay, all right. So now, if I represent them or try to represent them using a multi-layer perceptron, what we will do is, so this line actually, or this perceptron will represent S1. This perceptron will represent S2. Finally, this perceptron will actually combine them and classify this as 1. Okay. Another thing that I want you to notice that the nomenclature of this weights. Okay. So, this is considered as the first layer. This is called considered as a second layer. So, this is the first neuron of the first layer, this is the second neuron of the second layer, so the weight is W12. Okay, so this is how the nomenclature is. So similarly you can understand why it is W11, why it is W21 and all that. So can we go for more complex decision boundaries? Let's look at that. Now let's say that you are interested only in this region, so this triangle. Okay, so which is being formed by these two outer triangles. So again, what we can try to figure out is, maybe we will draw this line, we will draw this line, and we will draw this line. Okay, so then once we have drawn that, maybe we will try to draw another two lines, right? And try to find intersection of these two lines with the previously formed lines, all right? So that way, we'll proceed. So it turns out, if we instead of two layers, if we instead three layers here, maybe these three for these three lines and these two for these two lines, we can in the final layer find out this region as 1 and rest of the regions as 0. Okay, so this is kind of tells that if you stack perceptrons, so that becomes quite general purpose, and it can find decision regions of quite arbitrary irregular shape. Okay, so more formally, if we look at a neural network, so there will be one layer where the inputs are coming, which is called as your input layer, and here simply you are weighing the inputs. Okay, so that is being collected at one layer of neurons. Okay, so these are also perceptrons. Okay, and they can in turn be collected by another layer, and then finally at your output layer you are predicting whether the class is 1 or 0. Okay, so the most important thing that I want you to take a look is that this is called as the input layer, this is your output layer, and this is your hidden layer. So a multi-layer perceptron, which is more popularly called as MLP, will have one input layer, one output layer, and one to many hidden layers. Okay, all right. So what is the effect of hidden layer? So hidden layer has effects like number of levels in a decision tree, or like number of polynomial degrees in a regression problem or a support vector problem. Okay, so when you have three hidden neurons and these are your classes, it can find a decision boundary like this. If you have 6 hidden neurons, your decision boundary can be more irregular, and if you go to 20 hidden neurons, then your decision boundary can be something like this. So you can understand that hidden layer is also kind of a parameter of the model, which are also called as hyperparameters, and as we increase our neurons, our models also become more complex and they can also tend to overfit. So this is something which we'll discuss in later classes in more details. All right. Now let us look at perceptron learning and gradient descent, or even stochastic gradient descent. So let's look at the crucial lines. So if you remember, so this was what we were doing at our perceptron learning. So we were updating W new, okay, using W old, and how we are doing that? We were using the errors that we are making, and this was the learning rate, right? So this is how the weights were being updated so that you can find the correct straight line, all right? And what happens in a gradient descent, right? So you can also quickly look at our gradient descent lecture, but just to recap with you, Juliet, so this was what was happening in case of your gradient descent. Okay, so if you look at this formula, you know, it looks very similar, isn't it? So you have the same learning rate coming over here. However, you have something like this symbol. So do you remember what this was? So this was actually partial derivative of j with respect to wj. What was j? J was the cost function. Okay. Now, if we compare them, we see that both of them adjust the weight based on the error. Okay. So if you remember, actually j was also was measuring the error in case of your gradient descent. Okay. So both of them adjust the weight based on the error. Both of them uses learning rate. So you are using beta in both the cases. Perceptron learning works on absolute error, right? So this was the absolute error that we are working on, whereas gradient descent or SGD works on derivative of the error with respect to weight. Okay, so you are basically trying to see that, you know, if you increase the weight, okay, what is the change in the error? All right. However, if you think in a more generalized term, both works on a function of y and y dash, where y dash is your predicted value, right? So we can conclude that there is a lot of similarity in perceptron learning and your gradient descent. Okay, so let's now see that can we use perceptron for do a linear regression problem. So let's say you have different inputs coming in, right? Your x1, x2, x3 are your inputs, and these are the different weights that you are using, which are getting aggregated, and the perceptron uses some activation function, and then you get the final output, which is your predicted output, right? So let's look at the loss function that we are going to use over here. So the loss function that we are going to use over here is not your usual loss function. Okay, so we are going to use our linear regression loss function, which is residual sum of square, or if you use a 1 by n over here, you can also call this as mean square error or MAC. Okay, so you are not going to use the absolute error that we were seeing in a perceptron learning. All right, now activation function is not required, right? So if you remember, this yi dashed is nothing but your sigma, you know, wixi, right? So this was how a linear regression works. Okay, so you know, you don't need this activation function any longer. Okay, so this is not required. And the error function we have already discussed is the squared error. The errors are adjusted using gradient descent. So if you just make these three changes, right? You don't use the activation function, the error function, you use the squared error, and if you adjust the errors using gradient descent, instead of your perceptron learning, your perceptron can work as a linear regression model. Such a perceptron is also called as linear perceptron. Can we use it for logistic regression? Okay, so if you remember, so logistic regression essentially does a binary classification problem, and here what we need is we actually change the activation function. So the activation function in perceptron was a step function, if you remember, right? So this was a function like this. All right, so what we are going to do is we are going to use a logistic function, and the error function used is going to be cross entropy. Do not worry too much about it. So if you remember that when we were trying to find the parameters of logistic regression, we are using a method called as MLE, or maximum likelihood estimate. So if you actually try to use maximum likelihood estimate, you know, the loss function is nothing but this. Okay, so where again ti is your actual value and yi is the one that you are getting predicted. Okay, so you know this is the same thing as the logistic regression loss function. The errors are adjusted using gradient descent. So three changes again. You change the step function to a logistic function. You change the error function from your absolute value to cross entropy, okay, which comes from your maximum likelihood estimate, and you still adjust the weights using gradient descent, not by your perceptron learning algorithm. So this can work that way. Okay. Now, if you think that we have told there are one way to use perceptron to do the classification. So what we can do is we can use perceptron with usual error function, which is your absolute error. We can use the activation function as a step function, and you can use perceptron learning algorithm, and this can use as a binary classification model. Now, in logistic regression, what we are saying is we are using perceptron with a logistic activation function. We are using cross entropy as the loss function, and we are using gradient descent for weights. Okay, so we have got two options now, right? So which one we should use? Is there a benefit of using the option 2? So if you remember from our logistic regression class, so the logistic function looks something like this. So it will always have a value between 0 to 1. If it has a very low value, the value will be 0, and if it has a very high value which goes to maybe infinity, okay, then the value is close to 1. So this can be represented for predicting probability as a class probability can fall between 0 to 1. Now, if you remember, okay, so if I use this option 1, so essentially, your two classes are 0 and 1. So what you are trying to say is that if the predicted value is maybe 0.5, okay, then, the class is 1, else it is 0. So essentially what you are trying to do is you are trying to fit a line like this, okay. And you can see that in this particular case, this straight line does a very poor job, right? So for any case, so this is a tumor example. Okay, so there are two classes. So this is your tumor class. Okay, so this is your normal tumors, and this is your cancerous tumors. Okay, and this y-axis is actually your tumor size. All right. So you can see that using this option 1, you cannot actually distinguish these two classes. However, if you use option 2, it allows you to have a decision boundary like this, okay, which can actually segregate these two classes. Okay, so essentially this when we use option 1, this is a completely linear neuron. Using this logistic activation function, we can actually bring in some kind of non-linearity. Okay, so I hope I could give you some idea how perceptron can be so much generic purpose, and I could answer some of your queries. Please feel free to give more of your questions, and we'll be happy to answer them one by one. And if you have liked the video, please subscribe, please like our video, please give your comment. Thank you so much for watching this video, guys.